Alright, so this is a question from last year's exam, and I've just copied it verbatim from last year's exam. I'm going to make a few adjustments to it. I'll probably change the power and so forth, but it'll be something pretty similar to this. This is quite a tricky question, so we'll go through it together. So it starts off on the Argand plane in figure 10, the set of complex numbers of z equals cis theta is shown. The Argand diagram in figure 11 shows the solutions z1 through z5, which are the zeros of the polynomial z to the 5 take 1. Part A. Using de Moivre's theorem, write the zeros of z to the 5 take 1 in the exact polar form. Okay, so z to the 5 take 1 is 0, so we're going to solve that using de Moivre's theorem. And we've done this a fair bit. Equals 1, and then we'll have z is cis of 0 plus k2 pi to the power of 1 on 5. K is 0, 1, 2, 3, 4. This will give us cis of 0. Hang on, that's plus. So we'll have to get cis of 0, cis of 2 pi on 5, cis of 4 pi on 5, cis of 6 pi on 5, and cis of 8 pi on 5. And then we'll just change these such that they're within the constraints of cis of 0, cis of 2 pi on 5. This will be cis of minus 4 pi on 5, the conjugate pair of this one. This will be cis of minus 2 pi on 5. Okay, so they're the zeros. That's the answer to part A. Alright, now part B, we've got consider the function f of z, which is z squared plus z plus 1 plus 1 on z plus 1 on z squared, where z is cis theta. Okay, part A, show that the modulus of f of z is less than or equal to 5. Now this is an application of triangle inequality. I've said we're doing that in vectors, so we're going to leave that for now, but it's a good example of how they combine those techniques in exam questions. So we'll leave that part for now. Skip ahead to the next part. We can do this though. Find a value for z for which the modulus of this function equals 5. So when the modulus of this function equals 5, and all we're looking for, it's when z is 1, isn't it? 1 squared plus 1 plus 1 plus 1 plus 1 will give us a modulus of 5. So we get 1 mark there, we're just stating z equals 1, or z equals cis of 0, either of those would be fine. Alright, on to part C. Show that z to the 5 take 1, okay, so that's the polynomial that we started with, z to the 5 take away 1 is equal to z squared times z take 1 times f of z. Now all we're doing here is an expansion, okay, we're just going to start with the right hand side and expand this out. Start with the z to the 3, multiply that through. Now this is where, again, it helps to stagger. So I'm going to multiply the z to the 3 through, and then the z to the 2 through the line. So z to the 3 times z squared is equal to 5, plus z to the 4, plus z to the 3, plus that's going to be z to the 2, and then we're going to have plus z. Alright, we're going to multiply that z to the 3 through. These are all the terms I get. Next, we'll multiply the minus z squared through. Minus z squared times z squared, minus z to the 4. And so we're staggering them so that when we collect like terms, we can see that a number of them cancel. Minus z squared times z will be minus z to the 3, minus z squared, minus z, and then we'll be left with minus 1. These will cancel, and we're left with z to the 5 take 1. Alright, so that's part C. Hence, list the 4 zeros of f of z in polar form. Okay, so we're making a link between part A here, but so far what we've got is we've got this relationship, right? That z to the 5, we've demonstrated this is true, z to the 5 take 1 is equal to z squared times z take 1 times f of z. Now, if we want the zeros of f of z, I'm going to rearrange this to get f of z by itself. I'm going to divide both sides by this component. So we'll have z to the 5 take 1 on top of z squared times z take 1. Now, if we're going to find the zeros of this equation, so we can write f of z like this, and if we're finding the zeros of this equation, they're going to be the same as the zeros of this part, right? And we found those in part A. That was cis of 0, cis of, and we have plus or minus 2 pi or 5, and plus or minus 4 pi or 5. Now, I've got 5 zeros there. It says list the 4 zeros. Can anyone see why this is not a zero of this equation?
Because that equals 1, not 0.
Pardon?
Because it equals 1, not 0. It's can't be a root.
You're correct, but a zero is a number that we would put into this equation that would make this equation equal 0. That's what a zero means, yeah. What happens if we put it into the denominator here?
Undefined.
Undefined, okay, which means it's not a zero, it's an asymptote. It's an undefined at that point. So this is technically not one of the solutions for it. These are the 4 zeros that it's looking for in particular. Okay? So anyway, you get, I think it's only 1 mark here for listing those two. Alright, so that was C part 2. Now we're on to D. Using z equals cis of theta, show that f of z is real, f of z. So we can consider it in a couple of ways, f of z, but I think let's just focus on how we've got it expressed first, all right? And so I'm just going to substitute cis of theta into the original expression of z. So we have cis of theta squared plus cis of theta plus 1 plus 1 on cis of theta plus 1 on cis of theta squared. Okay, we'll apply De Moivre's theorem there, and we'll begin to simplify some of these. This will be cis of 2 theta, this will be cis of theta, this will be 1, this will be cis of minus theta, taking it to the top, and this will be cis of minus 2 theta. Alright, now to show that it's real, what we're doing then is we're going to focus on what's the imaginary components, what's the real components, by expanding it. This gives us cos of 2 theta plus I sine of 2 theta. Okay, that's what that one expands to. This gives us cos of theta plus I sine of theta. We'll put the plus 1 at the end, but then look what's going on here. We're going to have cos of minus theta plus I sine of minus theta. And what's cos of minus theta? Cos of theta. Okay, so that part's going to be positive. You can do it in one step if you want, and that part's going to be negative. Same with this term, cos of minus 2 theta plus I sine of minus 2 theta. And I said we put the plus 1 at the end, there. Okay, that's going to be cos of 2 theta, and this is going to be minus I sine of 2 theta plus 1. So then when we're looking along and collecting it, we're going to notice I sine 2 theta minus I sine 2 theta. I sine theta minus I sine theta. And so what are we left with? We've got 2 lots of cos 2 theta plus, and then we've got cos theta plus cos theta, plus 2 lots of cos theta, and then we've got plus 1. So that's what f of z is. There's no imaginary component to it. We've shown that it's all real. There's no I involved in it. That makes sense? Yeah. Okay. What's next? Show that f of z is this. So all we're doing is showing that this and what they've got expressed up there, 4 cos squared theta plus 2 cos theta take 1, are the same. So we're going to perform some substitution here for the double angle. I can see there's a double angle here, but there isn't in the new expression for f of z. So if we look at our formula sheets, cos 2 theta has a number of things we can substitute for it. So what is it? It's 2 cos squared theta take 1, I think. 1 take 2 sine squared theta, and then I think cos squared theta take sine squared theta. Am I right?
Yeah.
Excellent. Okay, so if we're looking at it, all right, we're going, I want to get rid of the double angle, but I want a cos squared, okay? We don't want any sine involved in it, so that sort of eliminates both of those substitutions. This is the one we're going to perform. So this is for part D, part 2. So we've already shown that this is what f of z is, and we're just going to take it a little bit further using the double angle substitution. So I'm going to have 2 cos squared theta take 1, where there's cos 2 theta. Okay, that's going to give us 4 cos squared theta take 2, plus 2 cos theta, plus 1, and then we just collect 4 cos squared theta, plus 2 cos theta, plus 1. Take 1. Alright, happy with all that collection? Is it the same?
Yeah.
Good. Okay, part 3, find the minimum value. Now here, this is a 1 mark question. So it's all building together, right? It's like we're built up here. It's like, hence, find the minimum value of that. All you have to do is graph that and g-solve the minimum, okay? Or you can think of it even like, I think this is a cool way of thinking of it. This is how I thought it when I first saw this question. This is very clearly a quadratic, plus 2 cos theta take 1. Okay? Like if we let a equal cos squared theta, we have 4a squared plus 2a take 1.
Would you not let it equal cos theta?
Cos theta, yeah. And even then, let's use x instead because we're not bringing up a formula in. Okay? Do you remember for a quadratic that the turning point occurs at minus b on 2a? Minus b on top of 2 lots of a. So that means our minimum occurs when x equals minus 2 on top of 2 times 4. So that's minus 2 on 8 minus a quarter. Alright, what is x? X is the cos value. So it's when the cos value is minus a quarter. Minus b on 2a. Alright, find the minimum value of f of z, good. And on figure 12, then we can just mark those on the plane here. So mark the value of z, for which f of z is a minimum. So here's the Argand plane. And we have the cos value is minus a quarter. So that's here and here, isn't it? Right? Those are the places where the cos value is minus a quarter. All right. Yeah, so there'll be one bit similar to that. I think for this part, rather than performing the quadratic substitution, just use your calculator, just G-solve it, okay? Graph that, G-solve the minimum, and then we'll indicate at what time we want. Does it all make sense, that question? Yeah. So it'd be a good one to put on your cheat sheet.
All 15 minutes of it.
Yeah.